Hey guys, hope you're well. So in one of the previous lessons, we learnt about a pulse, and we saw that a pulse was, for example, if I show you over here, it was a single disturbance that we can see. You see, it just makes one. But now, what if we had to try and make a whole lot of them? Okay, so if you had to try and make a whole lot of them, well then what's going to eventually happen is you're going to end up with something like this, which is what we call a wave. So we can say that a wave, or specifically we're actually talking about a transverse. And we'll talk about that a bit more just now. A transverse wave is now let's make it nice and easy for ourselves. It's a whole lot of pulses. Okay, that's all that a wave is if you take a whole bunch of pulses, you put them together, you get a wave. Why do we call it a transverse wave? Well, what I want you to quickly do is I'm gonna play this wave in slow motion, and I want you to keep your eye on this green particle over here. Okay, so I'm just going to fast forward this a little bit at a time, and I want you to look at that green particle. So have a look. I want you to see, is it going up and down, or is it going left and right? So have a look at that green particle. There it is again. See, if you keep looking at that green particle, is it going up and down or left and right? It's going up and down. So what we can say is that the particles, each of these is a particle, move. Or let me just say, for this example over here, the particles are going up and down. So the particles are going up and down. But what is the wave doing? Now let me play this for you in real time, and you can see, what is the wave doing? Is the wave going up and down or left and right? This whole thing is the wave. Okay, so look at that. How amazing is that? So what we can see is that the wave is going like that. It is moving to the right. So the wave is going to the right. So the particles are going up and down, but the wave is going to the right. So what angle does that make if you do that? Well, that is a 90-degree angle. So a transverse wave is when the particles and the wave move perpendicular. Perpendicular means 90 degrees. So we can say perpendicularly to one another. Okay? Now, I'll help you to understand this better. And I did show this when I was explaining what a transverse pulse is. But let's quickly go look at what happens when you go to a sports event at a stadium, and they start doing something called a Mexican wave. So here we have a Mexican wave. I'm going to play the video now. But what I want you to think about is in which direction the Mexican wave is going, and what are the people doing? Are they moving left and right, or are they going up and down? Okay, so let's have a look quickly. So here comes the Mexican wave. We can see the wave is coming towards us. So the wave is moving around the stadium. But look at these people. Look at this guy, for example. Look at what this guy's going to do. He's just going to stand up, and then the people are just going to sit down again. So the people are not moving left and right, but the wave is still going around the stadium. So that is amazing. That is a transverse wave. And so what we saw there with the Mexican wave was that the people were just going upwards. They would stand and then they would sit down, but the wave was able to go sideways. So that should help you to understand that is possible. So the people are the particles, and the actual Mexican wave is the wave. Okay, so that's what transverse means. Transverse wave. In later lessons, we're going to look at longitudinal waves where things are different. Now we're going to talk about some of the properties of waves. The first property I want to talk about is this distance from the middle line. Remember, your middle line is this line over here. Okay. Now the distance from that to the top, or you could also go from there to the bottom. That distance is called. I'm just trying to think where I can write it. Amplitude. Okay. Please remember that it's not from the top to the bottom. Whoops, I don't know what happened there. It's not from the top to the bottom. Okay. So that would be incorrect. It's, if you have the middle position and then you do a wave like that, then it is the distance from the middle to the top or from the middle to the bottom. It is not from the top to the bottom. Okay, must be from the middle. That is called the amplitude. The next thing I want to talk about is this part here at the top. We call that a crest. And then the part here at the bottom, we call that a trough, which is spelt quite weirdly like that. Okay, so we have crest and trough. The next one's really important, and learners get really confused with this one. Okay, so you see this part over, let's say for example, this part over here. Okay, that is not the same as this part over here, because this part is going up like that, whereas this part here, the wave is busy going down. Okay, so they're not doing the same thing. But if you look at this part here, that is exactly the same as this part over here, and you can see because that part is also going up. Okay, now if you had to then measure the distance between those two parts, that is called a wave length. It can be between any two parts that are the same. When I say the same, they must be in phase. Okay, so to measure the wavelength, it is the distance for one wave. And then let's just say here, remember to measure between points that are in phase. Okay, so for example, you could even measure the wavelength between, let's say for example, this one. Notice that here we are on our way up. Then you could also take, for example, that one, because we are on our way up. And then if you had to measure that distance over there, okay, well, it's more like over there actually, eh? Then that could be your wavelength, because this area and this area are in phase. Or maybe, for example, you want to take this part over here, which is exactly at the top. Then you could take that part over there, which is exactly at the top. And if you had to measure that distance, that is called wave length. And it has a symbol, lambda, like that. Okay, and we'll use that in calculations in the future. Now, I just want to show you a part where learners get confused about wavelength. So, for example, learners say, oh, okay, well, look at that part over there. And look at that part over there. They say that those are in phase. Now, they are in phase, but that's not a wavelength. The wavelength must only be, the wavelength must just be a single wave. So, for example, this one's also in phase. So you would want those two connected, okay? Because if you connect it all the way to there, then that is going to be one wavelength over here and another wavelength over there, and so that would have actually been two wavelengths. So for example, we could say that, let's say for example, E is in phase with, let's say it's in phase with I, because you see E is about to go like that. Or I'm not saying that point is going to go in that direction, but that's the way. That's what the wave's doing over there, and then over here the wave's doing that over there. So they're doing the same thing. So E and I are in phase. You could even say M is in phase as well. So you could say that E, I, and M are in phase. Okay, but that doesn't necessarily mean that they are all one wavelength. One wavelength is when you connect, for example, E and I. E and I is a wavelength, or you could connect I to M, and that would also be a wavelength. Okay, but if you had to connect all the way from E to M, that is not one wavelength, that would be two wavelengths. Okay, so from E to M is not a wavelength. So a wavelength must be, they must be in phase. So it means that they must be doing the same thing, but it must be the two that are next to each other that are in phase. Okay? The next thing I want to talk about is frequency and period. So listen carefully, because here's where you can, here's where learners often get very confused. So frequency is the number of waves per second. Okay, so frequency is the waves divided by the seconds. All right, now, and it's measured in hertz. That's its unit. Now, if you look at period, is the number of seconds per wave. So period is waves is seconds over waves. Oh, and I should also say here that the symbol for frequency is F. For period, the units will just be in seconds, and the symbol is actually a capital T. It's not a P, okay? So can you see that frequency and period are the opposites of each other? So there's this other formula that says that frequency is 1 over period, or period is 1 over frequency. Okay, so make sure you understand this. Now I'm going to quickly ask you some questions, little calculations, to make sure that you've grasped this part right here, because it's so important. And then after that, I'm going to show you the formula V equals to F times lambda, and that's where we'll end off our lesson. So let's quickly go do some calculations now with frequency and period. So here's our first one. Now remember that frequency, we said that frequency is waves, number of waves divided by number of seconds, whereas period, or we can just say T actually, is number of seconds divided by number of waves. So they tell us that 10 waves, so we have 10 waves, pass a specific point in 5 seconds, determine the frequency. So frequency is the number of waves divided by the number of seconds. And so that's going to be 10 waves divided by 5 seconds, and that gives us 2. And that would be measured in hertz. And then period, they said determine the period. Well, that is the number of seconds, well, let's just write here, seconds divided by the number of waves. And so that's going to be 5 divided by 10, which is a half, or 0.5 seconds. So you can just say seconds like that. Let's try another example. 8 waves pass... Now let's just quickly first go write our formula, It's waves divided by seconds, whereas period, let's use the symbol, T, is seconds divided by waves. So 8 waves, so we have 8 waves and 16 seconds. So the frequency is going to be 8 waves divided by 16 seconds, which is a half, or 0.5, and that's measured in hertz. For question B, so that was question A, question B, the period, well, the period is equal to the number of seconds divided by the number of waves, and that's going to be 16 seconds divided by 8, which is 2. You could also say that the T is equal to 1 over F, and so you could have said that the period is 1 over the frequency, which is 0.5, and that's going to equal to 2 seconds. I should say 2 seconds. Okay. I just like to put a little thing through there for my Z and for my S. Otherwise, it just looks a bit weird. Like this would look like a 2, and this would look like a 5. So I just like to do that. Okay. Right. Now we're just going to go talk about this formula over here, and we'll do a few calculations on that, and then we're done. V equals to F times lambda. I'm going to show you where that all comes from. Do you remember your basic formulas for distance, speed, and time? Well, we used to use this triangle, okay? And that gives us our formulas for distance, speed, and time. And so, for example, distance is equal to speed multiplied by time, speed is equal to distance over time, and time is equal to distance over speed. Now, I want us to focus in on this one quickly. So speed is distance over time. Now, when you think of distance, when we're talking about waves, I want you to think of wavelength, because that's a distance, right? So you could think of wavelength, for example. Now, wavelength has a symbol like this. That is what wavelength looks like. It's called lambda. So I'm going to say speed, but instead of saying speed, I'm going to change it to velocity. Okay? So velocity is equal to the distance, which we're going to rather call it wavelength. And then time. The only thing that we've spoken about so far that uses time is period. Can you remember? Here we spoke about period, and the units was seconds, which is the same as time. So I'm going to replace this with the symbol for period, which is a T. Now, the next thing I want you to remember is these two formulas that I showed you over here, okay? And so those formulas tell us that frequency, it should actually be a curved f, is 1 over t, or t is the same as 1 over f. So if you look carefully over here, there's a lambda. Now you can imagine that there's a 1 in the front there. That doesn't do any harm. So here we have 1 over t. So 1 over t is the same as f. And so we can then get the formula like that. And so whenever you are busy with waves, I want you to remember that you can use two different formulas, okay, depending on what they give you. You could either use normal speed equals to distance over time, or you can change it to using v equals to f lambda. Sometimes they're going to give you information that makes this formula easier, and sometimes they're going to give you information that makes that formula easier. So remember, when we looked at, in one of our earlier lessons, we looked at a pulse. Now with a pulse, you don't use this formula, because a pulse is not a wave, so you can't use wavelength. When you are busy with a pulse, you only use this formula. But when you are busy with a wave, which is when you have a whole bunch of pulses like this, then you can use this one or this one. Okay, now let's go do some calculations and practice those using that formula a bit, and then we'll be done with the lesson. So remember all of our different formulas now. So we've got two main formulas for waves, and so we've got that one, and then we can also use our distance, speed, and time formulas, depending on the information that they give us. So here they gave us a wave with a wavelength. Okay, so remember wavelength is lambda and has a period. Okay, so that's t, all right, of 5 seconds. Now we also know these formulas, f equals to 1 over t and t is equal to 1 over f. So they want us to find the speed. Now when they say speed, you can take that as v for velocity or s for speed, okay? For these calculations, they are the same. So we've got wavelength, okay? So we've got that. But we don't have, and this is what we're trying to calculate, the speed or the velocity, but we don't have the frequency. But we do have the period, so we could use this formula. So we could say that f is equal to 1 over t, and so the frequency is 1 over the period, which is 5, and so the frequency would be 0.2 hertz. So now we have frequency. And so now we can go and use that formula where we can say frequency multiplied by wavelength, and so the frequency would be 0.2, and the wavelength is 4 meters. And if we do the calculation, we should get 0.8 meters per second, because that is the units of speed or velocity. This one says calculate the speed of a wave. So they want us to calculate the speed, okay, of a wave with a wavelength, so that's lambda, that is supplied by a vibrating source with a frequency of 0.25. So we know that there's all these different formulas that we can now use. We can also use the distance, speed, and time formulas, and then we can also switch between period and frequency using these formulas. A wave that moves at a speed of 100 meters per second, okay, so that is a velocity or speed, has a wavelength of 40. Calculate the frequency. So we know that there's this formula. Now we know the velocity, we know the wavelength, but we need to find the frequency. So we could say that 100 is equal to f multiplied by the wavelength, which is 40. Then to get f by itself, you divide both sides by 40 and you end up with 100 divided by 40. And so the frequency would be equal to 2.5. So that'll be 2.5 hertz. This one says calculate the wavelength of a wave that has a speed of 10 meters per second and a frequency of 20. Okay, so we can just use that frequency, so we can just use this formula. Now we know the speed is 10, the frequency is 20, and we need to find the wavelength. So to get the wavelength by itself, you're going to divide both sides by 20, and you're going to get 10 over 20, and so that's going to be 0.5 meters, because the units of wavelength is in meters. This one says that a wave moves 21 meters, that's a distance, that's not the wavelength, okay? They didn't say that that's the wavelength. That's just how far the wave moves. That's distance, and that's time. Determine the speed. So now you wouldn't go use this formula. You would rather use the triangle with distance, speed, and time. So we know that if they want speed, then speed is equal to distance over time. And so speed is going to be equal to the distance, which is 21, over the time, which is 3, and that's going to be 7. And then the units of speed is m.s minus 1, so meters per second. A wave is moving 20 meters per second. Okay, so that's a speed or a velocity. How long will it take? So that's time that they're looking for. If it needs to move 50 meters, so that's a distance. Okay, so here we're going to use the distance, speed, time formulas once again. And so they want to know how long, so we need to work out time. So time is equal to distance over speed. Okay, so time is equal to distance over speed, and so that's going to be a distance of 50 and a speed of 20. And so if you had to work that out, you're going to end up with 2.5, and then that would be measured in seconds. Okay, just one or two, or I think 3 more examples, including this one. So it says, so 3 more included. So it's this one, and this one. Okay, so how far, that means distance, will a wave with a speed of 2 move in 3 seconds? That's time. So we're going to use our distance, speed, time formulas instead of using our v equals to f lambda formula. Now they're saying how far, so they want the distance. So distance is equal to speed multiplied by time. And so distance is equal to the speed, which is 2, multiplied by the time, which is 3, and that's going to give us 6 meters. These ones are interesting. I want to see if you can remember what to do. So it says that there are 9 waves, that's not wavelength, that just says 9 waves, pass a certain point in 3 seconds. Okay, so we have time. The wavelength is 3. Determine the speed. Okay, so we're going to use this formula because they're talking about wavelength, but we don't know what frequency is. Now, some of you are going to be like, yeah, but Kevin, can't we use this? But we don't know what this is. But can you remember the other thing I told you about frequency? Let's go back. We've also learned that frequency is the number of waves divided by seconds, and period is the number of seconds divided by waves. That's something you must remember. So we also know, once again, that frequency is the number of waves divided by number of seconds, and period is number of seconds divided by number of waves. So we can work out the frequency because we know the number of waves and we know the seconds, and so that's 3. Remember the units? Hertz. Now we can easily use this formula, and so that's just going to be f multiplied by lambda, and so frequency is 3. Lambda is that's the wavelength, that's 3 as well, and so that's going to give us 9 meters per second. One more example. It takes 4 seconds for 8 waves to pass a certain point. Determine the speed if the wavelength is 5. Okay, so we can use this formula again because we have the wavelength. They want us to calculate the velocity, this one over here, which is the same as speed, but we don't know frequency. But we know that frequency is 1 over t, but that's not going to help us. We also know that frequency is the number of waves divided by the number of seconds. And so that's going to be 8 waves and 4 seconds. And so that's going to be 2 hertz. And so we can then go use this formula by saying that it's 2 multiplied by the wavelength, which is 5. And so that's going to give us 10 meters per second.